Hello everyone, this is Dr. Hopkins with our next video where we're going to use redox chemistry that we've been learning in the last couple of videos in electrochemistry. I'll apply it to where we can actually use those electrons we're moving around. Okay, so electrochemistry, like I said, we're harnessing those electrons involved in a redox process. All right, so you have electron gaining and electron losing species. So one way we can do that is we can use a galvanic cell, or sometimes called a voltaic cell. It's essentially the same thing as a battery. Okay, a battery is a galvanic cell just hooked up to your whatever you want to run, your phone or your laptop or whatnot. And so let's start with some definitions of parts of the galvanic cell. We have the anode. Okay, so that's one of our electrodes is the anode. That's where the oxidation half reaction happens. And then you have the cathode, and that's where the reduction half reaction happens. And this is part of the reason why we learn how to balance redox reactions as half reactions, because we think about, when you set up a battery, you got this oxidation half and the reduction half. And so you've automatically kind of separate them that way. And then the units, if we're talking, when we're talking about electrochemistry, if we're talking about current, flow of electrons, it's amperes, so 1 amp is 1 coulomb per second. Coulomb is a unit of charge. Basically, the electronic charge is about 1.62, it is 1.62 times 10 to the minus 19 coulombs. And that's coulombs per second. And then the other unit we're going to deal with would be potential, which is voltage. Okay, so potential is the driving force behind electrochemical reactions, or driving force behind a battery, if you will. And a volt is a joule per coulomb, okay, in terms of units. All right, so let's look at a galvanic cell. So here is a really bad kind of sketch of a galvanic cell that I've drawn in this PowerPoint slide, where we have the anode in one, let's say, beaker, where we have maybe a zinc electrode, and that's where our oxidation is occurring. So our zinc is coming off the electrode after it gives up electrons into zinc 2+, which then is soluble into our solution. Now we're making that solution more positive. So we have a salt bridge in the middle, just represented on this line where I'll show, where we'll allow the nitrate ions to flow into the anode, and then the potassium ions from the solutions we've mixed in to flow into the cathode, and the cathode is where the reduction happens. So that copper electrode is negative. It has excess electrons that are then added to the copper 2+ to form more copper, and that's our reduction half. Okay, so we have a cathode and an anode. The difference between this and a redox, or just a standard redox reaction, is now we've separated both of the two reactions into two different electrodes, so that allows us to control the flow of the electrons through a battery, through a phone or a light bulb or whatever it might be. And so that's a design of a galvanic cell, or a crude look at a galvanic cell. So in order to determine whether we get electron flow in a galvanic cell, we need to assign a potential. So what's the potential of the electrons to be reduced or oxidized on each half reaction? And potential, by that I mean voltage. And in this case, we're not going to have an absolute value. What we're going to do is we're going to compare it to some standard reaction, which is the standard hydrogen electrode reduction half reaction. And that is 2 H pluses, so 2 protons, get 2 electrons, and we generate hydrogen gas. And that we assign as its reduction potential, because this is a reduction reaction the way it's drawn, as 0 volts. Okay, so that's the standard. And then we will just measure all the other potential, the reduction potentials versus that standard of 0. So some might be more negative, some might be more positive, but they're a comparison to the standard hydrogen electrodes. And you will look up and you can find tables of standard reduction potentials that we can use in determining a galvanic cell potential. So for our galvanic cell that I showed a couple slides ago, we've got our zinc and copper. So we have an oxidation and a reduction half. Okay, so now we look these up in a table. Now I'm not going to show a table of all these where we have to go through. So I've just looked them up myself. We have the zinc reduction potential and the copper reduction potential, and we have those as negative 0.76 and plus 0.34. That's great. Those are straight out of the table. What we want to do is determine the standard state cell potential. Okay, so that's for that galvanic cell with zinc and copper that I showed a couple slides ago. And the equation to do that is the cell potential is just the reduction potential at the cathode minus the reduction potential at the anode. So we have our reduction potentials. Which one was the cathode? The cathode was our copper, and the anode was our zinc. Okay, if we were to slide back to the slide, we would see that's the case. And so we put those numbers straight off the table into this, and you get a cell potential of 1.1 volts, plus 1.1 volts. So it is very, very important. You are using reduction potentials straight out of the table. You just put the numbers into the equation. You don't flip signs. The sign flipping is associated with the equation itself. And you don't multiply by stoichiometric coefficients. Now, in this case, it happened to be that we had 1 zinc, 1 copper. They're 2 electrons, and so they were 1 to 1. But if we had a stoichiometric coefficient, we don't put them into our cell potential calculation. And so what does that mean? What does that cell potential mean? If that cell potential is greater than 0, if it's positive, the reaction is spontaneous. This is what we would consider to be a good battery. Well, I mean, if you had them flipped, you'd be opposite. So if the cell potential is greater than 0, our process is spontaneous. Oops, sorry. If the cell potential is less than 0, the reaction is non-spontaneous. Now, the way we had them separated, if you wanted to make it spontaneous, you just flip the anode and the cathode around and you would turn around the cell potential. But the cell potential greater than 0 plus 1.1 is a spontaneous electrochemical process. And you were using this language, spontaneity, and we know from the beginning of the semester that spontaneity is related to delta G. So we're going to add that in. And actually, delta G is related to K. So we're going to have both free energies and equilibrium constants eventually from these electrochemical processes. So basically, the takeaways from the slide, we had the anode, the cathode defined as our oxidation or reduction. We can sum the cell potential to decide if it's a spontaneous or non-spontaneous electrochemical process that we've set up. And so next time we'll look at non-standard cells. So what happens when all of our concentrations aren't 1 molar? How does that change the cell potentials?